Welcome to Section 2 of Lecture 8. We will introduce deviation variables and use them to develop transfer function for first-order process. So when we first define Laplace transform, Laplace expression has no information at time less than 0 because the Laplace function was not defined at time less than 0. So when we make an input change to a process with a step, ramp, or some other input functions, we assume the input at time t less than 0 was 0. All changes begin at time 0. So when we use Laplace transform, it is often necessary to adjust the physical problem so that the equation we use has an initial steady-state condition to 0. Remember, Laplace transforms assume ft equals 0 at time less than 0. We adjust the problem by using deviation variables and use them before we take the Laplace transform. This slide demonstrates the concept of deviation variables for a fluid heater problem. In real world, the water temperature equals some values, let's say 40 degrees Celsius. But the Laplace cannot handle the initial value of 40 degrees C. So we use deviation variable to move the input to 0. After we implement the deviation variables, we can use Laplace transform. In this slide, we define deviation variables x, which is associated with input fluid temperature, and y associated with output fluid temperature. We write them as the difference of steady-state inlet temperature and with the steady-state outlet temperature. This is why it is important to write the steady-state equation and define the steady-state values. In this slide, we define deviation variables. When we use deviation variables, the initial condition simplified to x0 equals 0 and y0 equals 0. This is a good time to remind that after we solve the Laplace transform of the problem and find ft, we need to add back the steady-state values to get the correct answer. The unadjusted solution is based on the initial conditions being 0. But for physical problems, the initial conditions equal to 40 degrees Celsius, and we need to add it back in the end. Let's walk through an example. We are going to develop a temperature sensor for the fluid heater. We are going to use the dynamic lumped heat capacity analysis. Let's walk through an example. We are going to develop a temperature sensor to the fluid heater. We are going to use a dynamic lumped heat capacity analysis. We are going to assume the sensor is very small and the sensor temperature is uniform. Here is the term that describes the change of the sensor temperature with respect to time as the sensed temperature changes. The lumped heat capacity of sensor depends on the sensor density, volume, and the specific heat capacity of sensor materials. Since our sensor is going to be within a fluid, we will assume the heat exchange will be by convection. The sensor will gain heat when the fluid temperature T infinity is above the sensor temperature T. The sensor will lose heat when the fluid temperature T infinity is below the sensor temperature T. The convective heat transfer will depend on the convective transfer coefficient H and the surface area of the sensor A. Since heat exchange is through convection, it must equal to the heat change or loss by the sensor. We can equate the two terms. The negative sign is introduced because we are defining the direction of the convection heat flow by the state, and that is T infinite, is colder than the temperature of sensor. Then the sensor will lose heat. The initial sensor temperature is going to be T0. We write the steady-state equation, and the differential term is equal to 0 because there is no change in temperature at steady state. With this equation, we define the steady-state temperature to be Ts and the infinity steady-state fluid temperature to be T infinity S. We set the initial condition to equal to 0. Then we can use Laplace transforms. We introduce deviation variables x and y. X describes the foot temperature, and y describes the sensor temperature. We have the derivative term dt, so we need to take the derivative of the y deviation variable, which is dy dt. The next thing we need to do is to figure out how to insert deviation variables into the time-dependent differential equation. We have described in the convector heat transfer the change in sensor temperature. We do this by subtracting the steady-state equation when the time-dependent differential equation is shown in the upper right corner of this slide. It produces the equation shown, and we can reorganize to get the terms match the deviation variables. After reorganization, we get T minus Ts and T infinity minus T infinity S. Then we can substitute in the deviation variables to get h times a times y minus h times a times x equals minus rho times Cp times v times dy dt. This is the differential equation with the initial conditions x equals 0 and y equals 0 at time 0. And now we can use Laplace transforms. But before we use Laplace transform, we are going to divide both sides of the equation by negative 1 over HA. When we do the deviation, we produce the term called tau, which is equal to rho times Cp times V over HA. The unit of time constant tau is in seconds. The unit for time constant is always the units of time. We will talk more about the meaning of the time constant tau in the next video. Now we take the Laplace and use the initial conditions to find the transfer function. The detailed steps are in the course packet. This means the transfer function for our temperature sensor is 1 over tau s plus 1, which is y over xs, also gs. We rearrange it to be 1 over tau over s plus 1 over tau. Do you know why we rearrange to this form? Remember that tau is a constant, and 1 over tau form looks like equation 15 in the Laplace transform table. You will see this equation many times in the rest of the semester. This is a good time to remember something that transfer functions tell us in the previous video. Transfer function is the mathematical model that relates the output function y to the input function x. The function is the property of the system that is independent to the input function x. We can change the input x and find the response y with this equation. The function itself does not tell us anything about the physical problem. You will see this used in different physical problems. With the expression itself, you cannot tell where the problem comes from. This brings us to the end of this section. Please write down any questions you might have and bring them during the lecture or lab time.